Hello APC Mechanics students in Unit 5 Rotation, Class 7, 5.3, Atwood Machine again, Part 1. Section 1, massless versus massive pulley. Recall at the level of this course, we consider a special class of strings that are massless and inextensible in which tension is transmitted equally at all points. Now, this is a string under tension. Let's consider 2 points A and B. Now, at point A, we have tension TA, and at point B, we have tension TB. Both tensions are pointing away from both points. If the string is massless and inextensible, we have the tensions are equal. Now, recall that if the string loses tension, becomes loose in a specific dynamical system, the tension along the string will vanish, which means that T becomes 0. Recall from Unit 2 that the pulley is a simple machine used as a force magnifier. In Unit 2, we have studied massless pulley. In fact, we have two different types of pulleys. We have massless and we have massive. In this section, we will recall different concepts related to massless pulley and compare them for the massive one. So if you have a massless pulley, so let's compare the massless to the massive. So on the left, we have a massless pulley, and on the right, we have a massive pulley. Now that would be tensions T1 and T2. Independent of the state of motion, recall from Unit 2, we have that T1 would be equal to T2. Now how this can be compared to a massive pulley? In the case of a massive pulley, we have tensions T1 and T2. Now, if the acceleration is 0, which means that the pulley, which is massive, is not rotating, or rotating at a constant speed, that would be T1 is equal to T2. However, now if you have acceleration and due to the inertia that is encoded in the pulley itself, this would give us that the tensions T1 and T2 are not equal anymore, so we cannot equate them in order to solve for the acceleration of the system. For that, consider now Section 2 investigation for a massive pulley. Consider a massless and extensible string under tension that passes through the groove of a massless pulley. We connect two masses M1 and M2 such that M2 is greater than M1, producing tension T2 and tension T1. Hence, the masses M1 and M2 exert tensions T1 and T2 respectively. Because M2 is greater than M1, then the pulley will accelerate. We will erase the blocks from the drawing. Now, since the pulley is massless, which means M is equal to 0, then we have T2 is equal to T1. So first, here we're considering the case where the pulley is massless. Alright? The pulley and the two masses have the same acceleration. Let's tabulate our data. So we have the mass of the pulley, the acceleration, the tension T2, and the tension T1. Although the section here states we're investigating the case of a massive pulley, but till this moment we're considering the case where the pulley is massless. Now, massless pulley means M is equal to 0. We have an acceleration which can be determined using Newton's second law, and the tensions in this case are equal. Now here the numerics are based on the masses M1 and M2. Now we will inject mass to the pulley, hence it becomes massive. So mass has been injected. As you can notice that we have injected a mass along the rim, and we're neglecting the fact that now the pulley is massless, so it is massive. What would happen to the system? We record the observation. So here, by this one, I mean specifically that mass has a certain amount of mass has been injected to the pulley. Now, what will happen to the acceleration? Notice that the acceleration overall would decrease, and this is anticipated because we have injected more inertia to the system. However, now if you compare the values of the tensions T2 and T1, since we have acceleration, tensions T2 and T1, they are not equal anymore, and there is a difference between them. Now, let's suppose we're gonna inject more mass to the pulley, making it more inertial. So we have injected more mass to the pulley, and it has been indicated by 2 bars here. And the acceleration would decrease overall, and the difference between the tensions T2 and T1 would increase. So they will split even more. Now suppose we inject more mass, the acceleration would decrease overall, and the tensions T2 and T1 would become more, the difference will increase. Observations are recorded to generalize the results. What are the results? If the pulley becomes massive, the acceleration of the system decreases overall. This is 1, because as you can notice that as we inject more mass to the system, the acceleration decreases from 5 to 4 to 3 to 2, and this depends on how much mass we're injecting into the system, the tensions aren't equal anymore. As you can see that initially, if the pulley is massless, the tensions are perfectly equal. As we inject more mass to the system, there will be greater difference between the tensions T2 and T1. Finally, the tension along the falling mass becomes greater, that is T2 is greater than T1. So because the system is accelerated along this falling mass, then this tension is greater than this one. And now section 3, acceleration of a massive atwood machine. Consider a massless and inextensible string that passes through the groove of a massive pulley of rotational inertia I, moment of inertia I, and of mass capital M. So here, notice carefully, I didn't specify what is the rotational inertia of the pulley. The pulley might be a disk, and we know that the moment of inertia of a disk is given by half mr square, whereas the moment of inertia of a hoop, which is a ring, that would be mr square. Remember that a hoop is always more inertial than a disk. That's the system that we have. We connect to each end of the strings two massive objects of masses m1 and m2, with m1 is different than m2. The system consisting of the pulley mass m1 and m2 will accelerate and admit the same acceleration. Notice that although we have stated that if it's gonna accelerate this downward and this is upward, so the tension here would be different than here, but both three systems, m1, m2, and the pulley, they have the same acceleration, which is a. Okay, for this reason it has been denoted by a. If the mass m2 is greater than m1, then the mass m2 will accelerate downward, m1 will accelerate upward, and the pulley will rotate clockwise. The aim of this section is to derive the expression of the acceleration a of the system in terms of rotational inertia of the pulley I, mass m1, m2, and physical constants as appropriate, and this would be done by a blend between a Newton's second law for rotation and translation. Indeed, so let me denote this is the tension T1 and that would be the tension T2. T1 would be different than T2 simply because the pulley is massive, and more importantly, I didn't mention it here because it's accelerating, but I have denoted the acceleration on the system itself. However, they can be related to each other by applying Newton's second law to the pulley. So let's start by identifying the forces that act on the pulley. Whenever we're considering the pulley, we need to consider the rigid body diagram because we need to implement Newton's second law, and dimensions at this point is important to identify the torque. What are the forces that are acting on the pulley? We have its pull of gravity, which is along the center. We have the reaction at the pivot R. We have the tension T1, which is down, and the tension T2, which is also down. Now notice that the tension T1 represented at this point would be up, but the tension T1 at this point, if we're considering the rigid body diagram of the pulley, that would be down, T1 like that, and T2 here would be like that. And notice that I have represented T2 to be greater in magnitude compared to T1 because unbalanced torques, they will cause the pulley to rotate, and if it's rotating in this direction, T2 should be greater than T1, then everything makes sense at this point. Now let's apply Newton's second law for rotation for the pulley. Taking into consideration the positive direction is clockwise, then tau net is equal to I alpha, which means tau g plus tau r plus tau 1 plus tau 2 is equal to I multiplied by alpha. Now we can ignore the torque produced by the pull of gravity and the reaction at the pivot because they are zero. The line of action of the force passes through the pivot itself. Now tau 1 is minus the tension T1 multiplied by R. If here we're assuming that T1 and T2 are being tangentially applied to the pulley, so the torque produced by T1 would be minus T1R if this is the positive direction, and the torque produced by T2 would be plus T2 multiplied by R. And alpha, the angular acceleration, is given by A divided by R. Now replacing these in the equations, notice that I has been kept the same because we don't know the type of the pulley, for example, whether it's a disc or a hoop. And we can factor out R, and we divide. So here if R is taken to the other side down, that would be R square. Then the relation between the tensions is T2 minus T1 is equal to A multiplied by I divided by R square. What does I represent? I is the inertia of the pulley because now the pulley is massive. Now we will consider the forces that are acting on M1 because M1 is an object, and we will apply Newton's second law for translation. We will be interested in the FBD. What are the forces acting on M1? We have the pull of gravity down and the tension T1 up. Notice that T1 has been represented to be greater than M1G because it's accelerating upward. And now we can apply Newton's second law. F net is MA, taking the positive direction to be up. which means minus m1g plus t1 is m1a, which means t1 is equal to m1a plus m1g. Why this is important for us? Because remember that previously in the previous slide we have determined the relation between T1 and T2 with respect to the inertia. Previously we used to say that T1 is equal to T2 because the pulley is massless, but now the pulley is massive, so T1 and T2 are related by inertia. So we need to find T1 from Newton's second law, T2 from Newton's second law for translation, inject them in the equation that we have determined previously, and find the acceleration A of the system. Now then, the expression of the tension along the string of mass m1 is given by m1g plus m1a. Now what about the forces acting on m2? We have the pull of gravity is down and the tension T2 is up, and notice that I have represented m2g to be greater than T2 because it's accelerating downward. And now we're gonna apply Newton's second law, which is F net is ma, m2g plus T2 is m2a. The positive direction is taken to be down, then m2g minus T2 is m2a, which means that T2 is given by m2g minus m2a. Then the expression of the tension along the string of mass m2 is given by m2g minus m2a. Now we have these three equations. Basically we will replace T1 here and T2 here. We would get the following. And what I have done here is that, so I have replaced T2 by m2g minus m2a. We have a minus sign, so I have opened the bracket. We have m1g plus m1a. And now we can distribute the minus sign over the following two terms. And now we will move minus m2a and minus m1a to the other side. And what we're gonna do now is that I will flip the equation. Instead of reading it from left to right, I will read it from right to left, like that. And I will factor out A from the left member and G from the right member. We would have the following equation, and A eventually would be given by m2 minus m1 divided by m1 plus m2 plus I over r square. In the next lesson we're gonna investigate more about this expression, the expression of the acceleration, but let me elaborate a bit. So that would be the expression of the acceleration of a massive pulley for a simple Atwood massive pulley. Now, why in the numerator we have the masses m2 and m1? This is preceded by plus sign because it's helping the motion, that's opposing the motion. What about the denominator? We have m1 plus m2, and we have injected the mass due to the pulley itself. We know that the mass is being upgraded by inertia, but we cannot add or subtract physical quantities unless we have the same unit. Usually I, for example, is given by mr square. So in order to transform I to be whether I is given by mr square or I is given by half mr square, in order to convert I to have the dimension of the mass, we need to divide it by r square, which is the radius of the pulley. So here briefly, if the pulley is massive, this mass, which is symmetrical, is not helping or opposing the motion. For this reason, it will be absent from the numerator. However, we will inject it in the denominator in the form of rotational inertia divided by r square. And now for the rest of the video, we're gonna solve some exercises. Two blocks of one of mass m and one of mass 3m are connected by massless string over a pulley that is uniform disk of mass 2m and moment of inertia mr square. The two masses are released from rest and the masses accelerate as the pulley rotates. Assume there is negligible friction between the pulley and the axle. What is the linear acceleration A of the masses? So we know that here in this case they're asking me for the acceleration of the system, which is given by A, the mass which is causing the acceleration 3m minus m divided by the total mass of the system, which is m plus 3m, plus the rotational inertia given by mr square divided by the radius, which is r square, multiplied by g, that would be 2m divided by, now here what do we have? We have, so these cancel and that would be 5m multiplied by g. Now m would cancel, that would be 2 over 5 multiplied by g, making it C to be the correct answer. Okay. So here that's a mistake. That should be, I think, no, everything is correct. Why? Because if the moment of if the mass of the disk is 2m, then the moment of inertia is given by half 2m multiplied by r square, then 2 with half cancel, that would be mr square. Alright, this is apart from the solution. Now, two blocks of masses m1 and m2 are connected by a massless string that passes over a wheel of mass m as shown above. The string does not slip on the wheel and exerts forces T1 and T2 on the blocks. When the wheel is released from rest in the position shown, it undergoes an angular acceleration and rotates clockwise. Which of the following statements about T1 and T2 is correct? So if it's rotating like that, we know that this requires unbalanced torque. In particular, T2 should be greater than T1, which makes E to be the correct answer, and the reason is given by because unbalanced clockwise torque is needed to accelerate the wheel clockwise. And finally, the final exercise for today's video. Two blocks are joined by a light string that pass over the pulley as shown above, which has a radius r and moment of inertia I about its center. T1 and T2 are the tensions in the string on the either side of the pulley, and alpha is the angular acceleration of the pulley. Which of the following equations best describe the pulley's rotational motion during the time blocks accelerate? So if you notice carefully, they're asking us to relate the tensions to the rotational inertia, and this can be done by implementing Newton's second law for rotation. So remember, if this is a free response, we need to state carefully apply Newton's second law for rotation. So tau naught is equal to I multiplied by R. Now, what are the forces that acting on the pulley? We have its mass but produces no torque. We have the reaction at the axle, produces no torque. We're left with T1 and T2. Let's assuming they are being applied tangentially to the rim of the pulley, which means that the torque tau1 produced by T1 is minus T1R, and the torque tau2 produced by T2 is plus T2R, so that would be T2R minus T1R is equal to the rotational inertia, which is I multiplied by R. Sorry, that should be I multiplied by alpha. Now here, if we factor out R, that would be R T2 minus T1 is equal to I multiplied by alpha, which makes D to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.